example. Right? So the idea of this Excel example is I'm going to generate 3 sets of data randomly by Excel. And this, for each set of data, I will have 200 numbers. I generated those data from certain populations. Okay, so for example, the first data, I'm going to generate the data. So those data are extracted from a population, a Gaussian distributed population with with a population mean of 15.9 and the population standard deviation of 0.7. Okay. And I'm going to do the same thing to data set 2 and data set 3. And you can see that I'm trying to make, for when you compare data set 1 and data set 2, their population mean are different, right? But their standard deviation, population standard deviation are the same. So these 2 sets of data are coming from 2 populations, right? Even though their standard deviation are the same. And if you compare data 1 with data 3, they're from population standard deviation different, and the population mean are also different. Okay, so imagine that once I generate the 3 sets of data, and when you carry out the F-test for 1 and 2 and F-test for 1 and 3, for 1 and 2, definitely these 2 are the same, right? So if we carry out F-test for data 1 and 2, it should tell us these 2 data have the same mean, the same standard deviation, same variance, right? But if I do F-test for 1 and 3, they are not different. They are different. So the F-test should tell us they're different. I'm doing this just to showing that how reasonable this F-test is, okay? Before I start, does it make sense? Does the setting make sense?
How did you calculate that?
I'm sorry?
Professor, how did you calculate the F-test?
I haven't generated the data
yet.
I haven't generated the F-test, the random data yet. I will show you how to calculate F-test. I'm just asking that whether my setting makes sense. Like I'm trying to use randomly generated data to confirm the theory. Okay, if no more question, I'm going to generate the data. For randomly generating data, you will have to use the data analysis package. You go to data analysis and go to random number generation. Okay, and click OK. All right, so how many numbers do we want to generate? We want 200, and we want the distribution to be normal. So for all the tests, all the comparisons here, we're assuming a Gaussian distribution, normal distributed data. Okay, so you have to choose normal. And then the mean, I will put 15.9 with the standard deviation of 0.7. Okay, keep it in mind that all the mean and standard deviation here are population mean and standard deviation. Okay, so you're imagining you have a large group, infinite number of numbers in that group, and now I'm just taking randomly 200 numbers from that group. Okay, and I want it to be put in this area. Okay, with data set 1, and I'm going to do the same thing for data set 2. I just need to change the mean a little bit, 0.1, and put the value here. I think last time I was asked to make them larger. Make them larger. Data analysis. Can you see the operation clearly?
Yes.
Yeah.
Okay.
Yes.
So Professor,
15.
you're gonna use the data set to do the F-test, right?
Yes, I will do the F-test
Okay.
and the t-test. So this one I'm putting here. All right. Okay, so the first thing, let me delete the unnecessary columns. Okay. The first thing is I want to do the F-test between dataset 1 and dataset 2. How do we do that? We first calculate the experimental data, right? The calculated, F calculated. How do we calculate F, this value? Still recall what we just covered from the lecture?
FINV. FINV?
F is F calculated. FINV, yes, that's for the theoretical number. But we have to calculate the F calculated for our
Is it
Merriman.
S squared of Z1 over S squared of Z2?
Okay, and we said that we want to keep the larger value on the top and the smaller value in the bottom, right? So we have to know the variance first. How do we do that variance?
Square the standard deviation.
Okay, and how do we can use variance function directly to calculate the variance. So yeah, we have all the way. This is for 1, and for 2, it will be the same thing. You can actually copy and paste the function directly, okay? And we probably also want, so this is the variance. Okay, and we probably also want the mean, right? So I put X bar here, which will be average. Okay. And I do the same thing to the other 2 sets of data. Okay, now we know the 2 variants. Which one is larger? This one is larger, right? So we're going to put this as a numerator and this one as a denominator. So the F calculated will be E3. Oh, sorry. Is it E3? E3 divided by B3, right? And then for the theoretical value, which will be FINV, and then we have to put in the probability 0.05. What is the degree of freedom?
199.
Yes. 199, 199. Okay. I see there is question. Variance 1 square over variance 2 shouldn't be the variance for set of data 1. No, they're not. So when we are talking about the variance, we're talking about the sample, okay? That's why I keep saying that, keep in mind, those are population mean and population standard deviation. Yes, it's okay, it's okay. I know it's a little bit confusing. So those are our theoretical, like it's for the large population, but those are for the 200 data, 200 numbers. Okay. All right, so now we have the F calculated and F table. So what's the conclusion here?
Cannot reject null hypothesis.
Because FC is smaller than F table, right? Yeah. So they are not significant. Does that make sense? Right? Does that agree with our original data? Yes, right? Because we actually did generate the 2 sets of the data from the same standard deviation, right? And the F-test did tell us statistically these 2 are not different, even though the number from the sample variance look different, but statistically they are from the population with the same population standard deviation. Okay, now we already know that they are not the same. And how do we do the t-test? We're going to use data analysis tool again, and we're going to use t-test two sample assuming equal variances. Okay, and we click OK. Now, the t-test is the same with f-test. When you're using data analysis tool, you always want to put the higher value to be the first data and the lower value to be the second data. So in this case, we see the data set one, the average is 15.9, and data set 2, the average is 16.1, right? So the data set 2 is slightly larger, which is why we will choose data set 2 to be to be the sample. I'm going to change this to this, and this is going to be our second sample. And you can put 0 for the hypothesized mean difference, or you can put a slightly different value, but they will automatically calculate how different they are. And then the alpha value is the confidence level we want to set, right? 95%. And I want the output to be here. All right. So when you do the t-test of two samples assuming equal variances, you can see that our t-statistic, which is also t-calculated, is 2.4 something. Well, the t-critical is 1.96, okay? T-critical is theoretical number, or if you're doing one tail. So one tail and two tails are basically whether you're only considering one side of the Gaussian distribution, like whether the value is much larger or like much smaller. So you only consider one portion. The two tails that you're considering both sides of the Gaussian distribution. Okay? If I draw it here, one tail is only consider whether it's outside this range, but this one, the two tail is you're considering both sides. So you can imagine that if you know that your mean is definitely larger than the other mean, but you just want to make sure whether they're statistically different, you can just do one tail. But if they're very close and the standard deviation, the variance kind of cover each other, you probably will have to do two tails. It doesn't matter in this case because you can see that the t-statistic is larger than both the t-critical 1 and t-critical 2, right? So when we say that when t calculated is larger than theoretical value, what is the conclusion?
We can reject the null hypothesis.
We reject the null hypothesis, right? Meaning that these two data are actually significantly different, which is true, right? Because when we generate the data, the first one, average, the population mean is 15.9, while the second one is 16.1. Okay, does that make sense? Any questions still about this part? Okay,
No, I'm good.
Yes, oh good, okay. I'm going to upload this one to Canvas, and if you have time, you can go ahead and practice with doing f-test and t-test for data 1 and 3, and also for 2 and 3, and see how it works. Okay, and we have 10 minutes left.